All right, so in this video we're going to be talking about plane curves and parametric equations. So if you consider the path followed by an object that is propelled into the air at an angle of 45 degrees, if the initial velocity of the object is 48 feet per second, the object travels a parabolic path given by this quadratic right here. So when we look at this, we're seeing two pieces of information. We're seeing the height of the object, and we're seeing the distance that it's traveling. Now, to determine the time, so to say what time the object is at that height and at that distance, we can introduce a third variable t called the parameter. So if you write both x and y as functions of t, then x would be like your horizontal distance in regards to time, and then the y would be your vertical distance or your height in regards to time. So you would have these two different parametric equations. So this rectangular equation is a combination of these two parametric equations. You just can't quite see what the t value is in these or what the time is. So if you take this set of equations and you want to determine the position of the object at a specific time, we could plug in like t equals 0. And then you could find your horizontal distance and your vertical distance or your height. And so when the time is 0, then it hasn't traveled forward at all and it hasn't gone up at all. After 1 second or 1 minute or whatever the units are for time, we would find that the horizontal distance is 24 square root 2 and that height is 24 square root 2 minus 16. And we can see that looks to be the maximum of that parabola. So for this particular motion problem, x and y are continuous functions of t, and this path right here is called a plane curve. All right, and you'll see, we'll talk about this more, but you can see there's an arrow, and that tells you that the parabola is traveling this way, that as time continues, this is the position of the object. All right, so what is a parametric equation? If f and g are continuous functions of t, then x is a function of t and y is another function of t. And these are parametric equations, and t is called the parameter. When you sketch a curve represented by a set of parametric equations, you can plot the points on the xy plane. So that means that your time, your t, isn't really getting plotted. So we're not doing this in 3 dimensions, we're still doing it in 2 dimensions, just in terms of x and y. Each set of coordinates x, y is determined from a value chosen for the parameter of t, and that's important because we don't just start with -2, -1, 0, 1, 2, and kind of do a table that way. They will give you the time values, the t values that they want you to plug in. By plotting the points in order of t, the curve is traced out in a specific direction. And this specific direction is called the orientation of the curve. And we show this by using arrows. So time equals 0 is over here. Time equals 1 is right here, and so we can see that the curve is going this way. And that's why they used an arrow like that. All right, next page. So it says to sketch the curve described by the parametric equations. And so when we make a table here, we actually have 3 things that we're looking at. So we're going to have the t value, and we're going to have the x value that you get when you plug that t value in, and then we're going to have the y value that you get when you plug that t value in. And they're asking us to start at -2 and go to 3. So I'll do all the x values first. If I plug -2 in here, I get 4 minus 4 is 0. If I plug -1 in, I get 1 minus 4 is -3. If I plug 0 in, I get 0 minus 4 is -4. And then this would be -3, this would be 0. And then if I plug 3 in, 9 minus 4 is 5. So there's all of my x coordinates. And then for my y coordinates, I need to do t divided by 2. So negative 2 divided by 2 is negative 1. Negative 1 divided by 2 is negative 1/2. 0 divided by 2, I was actually going to write that, is just 0. 1 divided by 2 is 1/2. 2 divided by 2 is 1. 3 divided by 2 is 1.5. Or you could write 3/2, or you could write 1.5, whatever makes it easiest to graph. All right, so now when we graph this, we're graphing it in an xy plane, so we're going to ignore all those t values. And we're going to plot the point 0, negative 1, negative 3, negative 1/2, negative 4, 0, negative 3, positive 1/2, 0, 1, 5, 1.5. And when I plotted the points, they went this way. So I'm going to go ahead and draw an arrow, draw a couple in there. All right, let's try the next one. It says to sketch the curve described by these parametric equations. So we've got t and x and y. This time our interval is quite a bit smaller, and we do have a half in there. We have 1.5 at the end. So I'm going to go ahead and go by halves this time. All right, so I'm going to go ahead and plug these in. Well, maybe not plug them in my calculator. Let me see if I can, how I'll do mentally. So 4 times negative 1 squared, that's 4. 4 minus 4 is 0. Negative 1/2 squared is 1/4. 4 times 1/4 is 1. 1 minus 4 is negative 3. 0, that's negative 4, that's easy. Negative 3 and 0, since those are the same numbers. And then 3/2 squared would be 9/4. 4 times 9/4 is 9 minus 4, so that's 5. So, yeah, look at that. We've got the exact same x values we had before. And then y is just t, so I'm going to just go ahead and copy these over here. Okay, so if we graph these, again, I'm not graphing the t values, just the x and the y. So we've got 0, negative 1, negative 3, negative 1/2, negative 4, 0, negative 3, positive 1/2, 0, 1, 5, 3/2. So if you look at this, the picture looks exactly the same. And we might think that these graphs were identical, except that we do know that our times were different, our equations were different, our times were different. So what we'll notice is that even though the graph is the same, or same curve, I guess I could say, our time was quicker. We had a quicker time. So this up here, it took 5 seconds from negative 2 to 3 to graph the curve, or to have the object move in those positions. Here it took 2.5 seconds to do the same thing. So this was done in half the time. The orientation of the graph is the same. All right, for the next one, we're going to go ahead and do this in our calculator. So if you look at your calculator to graph parametric equations, we're going to hit the mode button. And down here, my graph is in function form, like functions right now. I want to do parametric equations instead of functions. So I'm going over to PAR, press enter. So now when you hit the y equals button, it's going to ask you for 2 different equations, one in terms of x, one in terms of y. Well, both in terms of t technically. One as x equals, one as y equals. So x equals 4t squared. And notice I'm still hitting the x button. It's just not using x since I'm not in function notation anymore. Now I'm doing parametric, so it's doing t for me instead. So 4t squared minus 8t. I missed the minus. and then y was 1 minus t. So I'm going to hit window. For my window, the minimum t value I have is negative 1/2. My maximum t value is going to be 2, and I'm going to go ahead and have it go by 0.5s. I'm going to have it go by halves. And then I'm not exactly sure how big this graph is going to be, so I'm going to go ahead and just leave the x values of negative 10 and 10, kind of like normal, and just let it go. So when I graph this, I can see it's actually the exact same shape as before. So I'm being tricky here with these notes. If you want to see what order the points go in, then I'm going to go ahead and hit second window. I'm going to set my table. I'm going to have my table start at negative 1/2, and I'm going to have it go by 0.5s because that's a good way to set this up. So if you look at the table, second graph, you can see that we're using the same points. So we have 5, 1.5, and then 0, 1, and then negative 3, 1/2, negative 4, 0, negative 3, negative 1/2, 0, negative 1. You can see that we did the same points, we just did them in backwards order. So it means that this graph looks the same, but the orientation is backwards. Right, so 3 equations that appeared to be completely different actually gave us the same graph 3 times. So it's kind of interesting just to notice that the position can kind of move back and forth. All right, example 4 says to change the parametric equation into a rectangular equation. So what they mean by that is we don't want to have a value for t anymore. We want only x's and y's. So here your goal typically is to get a recognizable equation. For most of us, that means that our final equation is going to be written as y equals something. So that means that when we isolate the t, we typically want to do that in the x equation. So I'm going to isolate t in the x equation so I can plug it into the y equation. This might remind you of systems of equations back in the day where you would isolate one variable so you could plug it into the other one. So I'm going to start with x equals t squared minus 4. And then to solve for t, I'm going to go ahead and add 4 to the other side. And then to solve for t, I'll go ahead and square root each side. So t equals plus or minus the square root of x plus 4. Got to make sure I get that plus minus in there because those are the actual solutions. And then it says y equals t divided by 2. So plus minus x plus 4 divided by 2. Now, not quite the proper form. This is actually 2 different equations for y. But this is a square root curve, so it would give us like the top part of a square root and the bottom part of a square root. So if you can picture it, this is actually a sideways parabola. Now when we write sideways parabolas, to get away from this plus minus, we typically have them written as x equals equations. So this is a unique circumstance in that an x equals equation is also recognizable here. So I'm going to go ahead and show you guys what would have happened if we had used the other equation instead. So here, if we're going to isolate the t, we would multiply 2 to the other side and get 2y equals t. And then we could go ahead and plug that in. So x equals 2y squared minus 4, which is x equals 4y squared minus 4. And that might look a little bit more recognizable as a sideways parabola, but that's what it is. So here we're going to write a little note to ourselves that our goal is a recognizable equation. So you want to be able to look at your answer and say, yeah, that's a parabola, yes, that's a rational function, yes, that's something. All right, now example 5, we're going to do it. It's going to feel tricky at first. It's basically a little trick you have to memorize because I think in a lot of situations most people wouldn't think of it. So here we're going to remember that cos squared plus sine squared equals 1. And since these are in terms of t, I'm going to go ahead and write my formula in terms of t. So what this notation really means is it really means that you're taking your cos t and squaring it, and you're taking your sine t and you're squaring it. That's what that Pythagorean identity really means. So here, if we are able to isolate cos t, then we can make a substitution. So if I have x equals 3 cos t, then I can go ahead and divide by 3. And so I know that x over 3 equals cos t. So I can take the cos t and substitute in an x divided by 3 in its place. And now I've eliminated the t for that parameter. Or I've eliminated the parameter for that equation. Over here I could do the same thing. I could divide the 4 over to the other side, and then my sine t would be isolated. So I'm going to go ahead and write y divided by 4 squared. And if I get rid of the parentheses, that would give me x squared over 9 plus y squared over 16 equals 1. And depending on how well you remember conics, you may or may not recognize that that is an ellipse. So that is, in fact, a recognizable equation. All right. The next little thing that we're going to talk about is the domain and range of these as you kind of switch back and forth between equations. So the range of x and y implied by the parametric equations may be altered by the change to the rectangular form. When you do the conversion, you might find kind of like up here, if I had only used the plus version, then I would have been skipping half of my values. So in such instances as that, the domain of the rectangular equation must be adjusted so that the graph matches the graph of the parametric equations. All right, so I'm going to go ahead and get this written in rectangular form. So like normal, I'm going to go ahead and start with the x equation and solve for t. So x equals the square root of t plus 1. I'm going to square it. So x squared equals t plus 1, and then go ahead and minus the 1 over. And then I can go ahead and take that and substitute it in for t in the other equation. So it looks like we have the parabola 2x squared minus 1. That's our parabola. Now, if we think about this, we know that because we have a square root there, you can't have a negative underneath the square root. So that means that t plus 1 has to be greater than or equal to 0. You can take the square root of 0, you just can't take the square root of a negative. So that means that t had to be greater than or equal to negative 1. So right here, if this is where t is isolated, then t has to be greater than or equal to negative 1, and since t equals x squared minus 1, then x squared minus 1 also has to be greater than or equal to negative 1. So if I go ahead and solve that, I get x squared is greater than or equal to 0, and so x is greater than or equal to 0. So when we graph this parabola, we are only going to use the right side of it. We are only going to use values where x could equal 0. So if I plug 0 in for that, I get negative 1. If I plug 1 in for that, I get 1. If I plug 2 in, I get 7. And here I'm graphing a rectangular equation. I'm not graphing the parametric equation, so I don't need to worry about the arrows this time to show the orientation. I'm just going to go ahead and draw my half of a parabola. All right, so I only drew the right side, and that was because I had some limitations in my parametric equation that I had to keep when I wrote that equation in the rectangular form. All right, and we're going to go ahead and leave the rest of the notes to look at tomorrow in class.